In this video, we will look at one-sample hypothesis tests when sigma, the population standard deviation, is unknown. This is the normal situation because if we had enough information to calculate sigma, we could also calculate the population mean, making significance tests unnecessary. I'm going to explain three examples of hypothesis tests. One example uses a two-tailed test. A second example uses a one-tailed test that rejects in the lower tail, and a third example uses a one-tailed test rejecting in the upper tail. In the first example, we have a situation where a machine is supposed to fill cups with 12 ounces of liquid. If the machine puts too much or too little liquid into the cups, the process is not operating as designed. A random sample of 15 cups has a sample mean of 11.6 ounces with a sample standard deviation of 0.9 ounce. At the 0.05 level of significance, is the machine operating properly? Since we're trying to find out if the cups are being filled with too much or too little liquid, this calls for a two-tailed test, where we're willing to reject the null hypothesis if the sample mean is too small or too large. The null hypothesis is mu equals 12. By the way, you always put the equal sign in the null hypothesis and never put it in the alternate. The alternative hypothesis is mu is not equal to 12. In hypothesis testing, the critical value or values are the values of the test statistic that lead us to reject the null hypothesis. Alpha is the level of significance, and we put half of alpha in each tail with the two-tailed test. In this problem, alpha equals 0.05 and the sample size equals 15. The line of code that reads QT, open parenthesis, P equals 1 minus alpha over 2, df equals n minus 1, puts alpha over 2, or 0.025, in the upper tail. This t-value is 2.145. The equivalent value in the lower tail is a negative 2.145. So there are two critical values, plus and minus 2.145. If the calculated value of the test statistic is between these two critical values, we do not reject the null hypothesis. The tsum.test in the BSDA package can be used to run hypothesis tests when you know the sample mean, standard deviation, and sample size. Go to !tsum.test for information on the tsum.test function. The first argument is mean.x, and this is where you enter the sample mean. The next argument is s.x, this is the sample standard deviation. Next is n.x, which is the sample size. The alternative argument is two-sided. This tells the computer to run two-tailed tests. The argument mu equals 12 tells the computer that the hypothesized value of the population mean equals 12. The conf.level equals 0.95 tells the computer to find 95% confidence intervals, and this is consistent with the 0.05 level of significance. The output tells you t equals minus 1.7213. This is the calculated value of the test statistic. This is the number you compare to the critical values. Recall, we found the critical values to be minus 2.145 and positive 2.145. The calculated value of the test statistic is between the critical values, so we do not reject the null hypothesis. The p-value is 0.1072. This is the combined area to the left of t equals minus 1.7213 and to the right of positive 1.7213. This is higher than alpha of 0.05, and this also leads us not to reject the null hypothesis. The 95% confidence interval estimates the population mean to be between 11.11 and 12.10. The hypothesized population mean is between the confidence limits, which is consistent with not rejecting the null. The second example uses a sample of 200 observations with a sample mean of 477.155 and a sample standard deviation of 246.2169. We want to find out if the population mean is less than 500 at the 0.01 level of significance. This calls for a one-tailed test rejecting in the lower tail. The null hypothesis is if the population mean equals or exceeds 500. The alternate is mu is less than 500. Since this test rejects in the lower tail, the critical value is negative. The t-value of minus 2.345 puts 0.01 in the lower tail. This is the critical value. We compare the calculated value of the test statistic to the critical value, and if it's less than the critical value, we reject the null hypothesis. We tell R the alternate equals less. Because this is the alternate hypothesis, the 99% confidence level is consistent with alpha 0.01. The calculated value of the test statistic is minus 131, rounded. This is greater than the critical value, so we do not reject the null. The p-value is 0.095 rounded. This is greater than alpha, and the one-sided confidence interval tells us that mu may be as large as 518 rounded. All of these indicate that the null hypothesis should not be rejected. The third example has an alternative hypothesis that mu is greater than 8. This is a one-tailed test rejecting in the upper tail. The critical value at alpha of 0.10 is t equals 1.318. The calculated value of the test statistic equals 2.31, and the p-value is 0.0048. The p-value in this problem is the area under a t-distribution with 24 degrees of freedom that is greater than the calculated value of the test statistic. The confidence interval suggests that mu may be greater than 8.05 rounded. We reject the null at mu is less than or equal to 8. In this video, we looked at one sample test of means when sigma, the population standard deviation, is unknown. We used the tsum.test function in the BSDA package to perform hypothesis tests and find confidence intervals with two-tailed tests, with one-tailed test rejecting in the lower tail, and with one-tailed test rejecting in the upper tail. Thanks for watching, and please let me know if you have any questions.